Okay, well, good afternoon, everyone. On behalf of our speaker, Zoe Brooks, I would like to welcome you to today's webinar. My name is Raymond Gertz, and I am co-founder and lead software developer for Awesome Numbers. Awesome Numbers is pleased to be the sponsor of today's webinar. Awesome Numbers Inc. offers the IQCP ToolKit, including our Prof. Zoe's risk simulator, to everyone from the medical director to the bench MLS, and our quality optimizer software is for license to QC software companies and as an online service available directly to laboratories. Awesome Numbers Inc. is also the platinum sponsor of Awesome U, where Zoe Brooks hosts online resources, discussions, projects, and courses. Our goal is to make a quantifiable difference in patient care. Here are just a few housekeeping items for today's webinar. As we go along, please feel free to submit your questions in the questions box on your GoToWebinar menu. Zoe will answer questions at the end. Now I would like to introduce Zoe Brooks. Many of you already know Zoe from her workshops or her book, Performance-Driven Quality Control, or as a speaker or her roundtables at AACC. If you aren't yet familiar with Zoe, I would like to introduce her as someone who cares passionately about quality management. Zoe has been in the medical lab quality control industry for over 35 years and has worked in many different roles. And now I would like to turn it over to Zoe.
Thank you very much, Ray, and thank you folks for attending today. I threw this one together in a bit of a hurry because there's so much talk going on about IQCP, and specifically there was a great discussion on LinkedIn about QC frequency. So I'm glad you found time in your busy schedules to join us. What Ray alluded to there is, yes, I have been fascinated with quality control for years. I have spent since 1974 every day focused on medical lab quality, and since '87 about exclusively on quality. I take the statistics apart, I put them back together, I model real data, and between decades of frontline lab management, decades of studying, and now decades of software refinement that Ray brings to the table, and the simulator we're going to show you today has actually evolved over almost 20 years as the technology and the science has evolved. So today we're actually going to show you what I think qualifies as a new QC process. We'll go through introduction, regulations, definitions, IQCP in theory, IQCP in practice, and where to from here. After this webinar, you will be able to clarify the fundamentals of risk management in IQCP. That's a lofty goal. I should mention before we go further, this is for numerical tests only. So if you're here from blood bank or microbiology, thank you so much, but I have nothing for you. This is for the 80% of tests that have numerical results. So for these tests, clarify the fundamentals of risk management in IQCP, envision and explain how and why patient risk and cost varies with method accuracy and precision. The acceptability of risk varies with medical goals and acceptable risk level. And that idea of the acceptable risk level is what's new. We're not going to talk about sigma. There's a video up online that can explain what's going on with 4 different ways to measure sigma. We're not going to get into that today. We're going to talk about what works. Show you how to select a full QC strategy and modify QC frequency to ensure acceptable patient risk. And these are my favorite words in all of this regulation, is that at the least, the ability of QC procedures to detect medically unreliable results should be evaluated. So, but first the big picture, and we're going to fly through this fairly quickly. What is IQCP? What is risk management? What must you do? What should you do? What can you do? And how do you know you've done it right? IQCP is risk management. This memo came out in 2013, and it's the best document I've seen that actually describes what IQCP is. This is the list they sent to the inspectors of what they'll be looking for. So IQCP is a new quality option for labs based on risk management. What is risk management? It's a systematic application of management policies, procedures, and practices to the task of analyzing, evaluating, controlling, and monitoring risk. At the least, the ability to detect medically allowable error should be evaluated. Risk management adds the fifth element to quality control. I've taught quality control for decades now, and I've always taught it with there are four key numbers that drive quality. The true value, the current mean that you use to calculate accuracy, the SD that drives precision, and the allowable error limit or the medical goal. But now you add acceptable risk, and this fifth element changes everything. It changes what you see, and it changes what you can do. What must you do? You must ensure the accuracy and reliability of test results, and that test result quality is appropriate for patient care. This document, by the way, is posted in the handouts with the webinar, and both of these are available online. I'll comment just to say, this I would describe as the minimum, this I would recommend. What should you do? Read the glossary, follow the flowcharts. They got it right. I was part of this committee, not as involved as I would have liked to have been, but they got it right. With medical goals and acceptable risk levels, risk management is black and white. Here's how it works in theory. There are two components to risk management. You have the current risk of the analytical process, and this is what we've managed for years and years and years. We do key staff training, we do method validation, we do daily QC, proficiency testing, we do inspections, we do accreditation, and then you have the potential risk of the QC process. If all of this fails, if the analytical process fails, you rely on the QC process to prevent harm to patients. This answers the question, is my risk acceptable today? This answers the question, will my risk still be acceptable if the method fails tomorrow? Here's what happens. There's an initiating cause, something goes wrong, the system fails, it generates an incorrect result. The question becomes, will that result be reported or not? These are potential failure modes that are listed in EP23. Now, you could start by saying, can I identify every single one of these failure modes without using stable sample QC? If you can, then the rest of this lecture has nothing to offer you, because this is dealing with that last line of defense that is the statistical QC sample or the stable QC sample that you use to mirror your patient samples and to make sure your patients are working. So regardless of what you've done to prevent, regardless of the lists and checklists, if a final error gets through, will that QC sample detect it? Failure is, in the broadest sense, a system that doesn't meet the user's expectations. In the lab sense, it means it is unable to perform its intended functions satisfactorily or within specified performance limits. Performance limits have been part of theory forever. An incorrect result is a result that doesn't meet the requirements for its intended medical use. In the case of quantitative test procedures, a result with a failure of measurement that exceeds a limit based on medical utility. It is all about preventing patients from medical harm. If you have a verified effective risk management process, it will put a block up here and stop that incorrect result being reported. Failures in the testing system impact all patients tested until the failure is corrected. We talk a lot about pre-analytical, analytical, and post-analytical failures. The big difference is that pre-analytical and post-analytical failures tend to affect one patient, a small batch of patients. But when something goes wrong with the analytical process, it churns out potentially thousands of unacceptable results that can lead to misdiagnosis, that can lead to hazardous medical actions, that can lead to patients being harmed. What can you do? Well, for all tests that create numerical results and rely on stable sample QC, when the lab director sets the medical goal and acceptable risk level, the risk management process can be evaluated, improved, and essentially automated if you have those numbers. So remember the 80-20 rule. I guessed at this, but I think about 80% of the tests we perform create numerical results, rely on stable sample QC to detect changes in accuracy or precision that could produce medically unreliable results that harm patients. Those are the ones we're talking about today. So here's a thought. Think for yourself. That's really the challenge they're offering you. You know, you've been trained, you know what's going on with QC, you know about risk management. I am so terribly tired of business people, not close business people, but if you're looking at peripherals, I hear so many times nobody in the lab cares about patient risk. But I know we do, but we've developed some strange habits. Ask yourself this question, or consider asking a patient this question. Is it really okay to report patient results without checking the QC first? If you try asking patients that, they tend to get a funny look on their face. So what IQCP says and risk management says is you can do QC any way you want as long as you can prove that it works. So the question becomes, what do you want to do? The minimum to meet requirements or the maximum to improve quality? If you're after the minimum to meet requirements, that's well documented elsewhere. We're not going to talk about it. The flowcharts in this document are absolutely brilliant. You estimate risk, you evaluate risk, you do everything, so you control and monitor your risk, you do everything you can to prevent risk, you investigate failures, you reduce risk. They left one incredibly important block off of this. You have to minimize the risk and harm from medically unreliable results reported. They're missing the fact that right now, medically unreliable results are getting through our QC systems, and they are being reported, and that's well documented in many studies. Do you know that CLIA says, in the event of a testing process failure, has the laboratory evaluated all patient test results since the last acceptable quality control? That came from that IQCP checklist, by the way, that you can download. So if you're going to do QC right, if you've reported medically unreliable results, if your QC detects an error, you're also going to look back. What we're going to show you today is a risk simulator to understand, model, practice, teach, and verify IQCP. It's that fifth element. It makes all the difference in the world. Medical goals set a clear dividing line between reliable and medically unreliable results. Between, if a result is this close, yes, my doctors can rely on it to reach a good result most of the time. Beyond that, it's not always going to deceive you, but it's not reliable. So there's a black and white line between medically reliable and medically unreliable results. Acceptable risk levels. Medical goals have been recommended for over 40 years. Acceptable risk levels are new. They change QC practice and they reveal new understanding. There are two steps to answering the question, is risk okay? First, you have to perform a risk analysis. How much risk exists? Then you perform a risk evaluation. Is the measured risk less than the acceptable risk? You set medical goals. Within these limits, results are medically reliable. Beyond those limits, results are medically unreliable. We're going to show you risk bars that show the current risk against the true value, which comes best from your peer mean, and the allowable error limits. But we also model unacceptable risk, and the question becomes, how many medically unreliable results are you willing to report each month? Will QC detect unacceptable risk? If you're in a fairly large setting, you can actually do this on a large-scale basis. You can say, for these analytes, in these clinical settings, I'm going to use either the published standard, so for glucose, you can say I'm going to use the diabetes standard. For cholesterol, better yet, you're going to use the lab policy that you've worked out with your local clinicians to say, yes, this level of quality and this risk level is acceptable. And then you say, what's the acceptable patient risk? For the last 30 years, we've been taught that a 5% risk level is acceptable. As a matter of fact, Mosby's Medical Dictionary says that 1 result in 20, when they define allowable error, they essentially say that 1 lab result in 20 can be medically useless. Yet 90%, 95% of glucose methods can be maintained at a 0.1% risk. When you manage risk, you see entirely new things. How can that work in practice? It's fine in theory, and we've seen it in theory for years. What's available now, after all these many, many years, is Prof. Zoe's Risk Simulator. This is what Ray referred to earlier in the IQCP ToolKit. So you have 4 steps to go through, and the risk manager, the person who's trained to go through this, would use this process. They would evaluate the current risk. So you enter the data and evaluate the risk. But you can also, this is a teaching tool. You can model risk management in theory. So this is a tool not only to use in practice, but if you're looking at recommended processes to set up QC rules and QC frequency, you can model any of those here. You can select an optimized process. You can compare the mathematically optimized QC process recommended here with what you're doing now, and you can come into a final assessment that says, what are you going to do? Is risk acceptable, and what are you going to do about it? Then you have 3 reports to refer to. The only one of these we're going to look at today is the risk assessor's text report. That simply answers the question, is risk acceptable, yes or no? When you plug in these 1, 2, 3, 4, 5 magic numbers along with the results per month, the software will tell you, is risk acceptable? What is the current risk? What is the number of medically unreliable results currently being reported? And what's the margin for error? It also shows you the current risk and unacceptable risk on risk bars. And again, the question is, can you draw the line? This is a really good method. Well, you see a risk evaluation chart that answers the question, is this method acceptable? So it again shows the true value and the allowable error limits. And as long as all your results here are within your medical goals, the method is acceptable. The change chart that you've always known as a QC or Levy-Jennings chart answers the only question a QC chart can ever answer, and that is the method stable? We can then come in and simulate a failure. So what we do with every single QC sample is after this line, there are 20 points, and one of them will fail. So that means the risk after here is unacceptable. Can you draw a line between where you are now and unacceptable risk, and will QC detect that change? And in this instance, it will. Margin for error is the number of SDs the mean can shift before risk becomes unacceptable. Patient risk and both patient risk and QC effectiveness vary with the margin for error. Margin for error takes into account those 5 numbers, and from the margin for error, you can determine the mathematically optimum QC process to meet your acceptable risk criteria. So where sigma is the number of SDs the mean can move until the allowable error limit, margin for error auto-adjusts based on your acceptable risk level. If you want to say, I want to detect risk when it's only 0.1% failure, your margin for error will be smaller than if you're willing to accept a 5% failure. Margin for error takes all the theory and combines it into one number for you. So as you go along, as you change those numbers, you can see that the pass and the fail criteria will change. The current risk, the number of results that currently fail, so both the percentage and the number of medically unreliable results per month can be calculated from those numbers, and you can see how the margin for error varies. When the margin for error varies, you're going to change your QC process. So we start with a baseline case. This is our very good case. It has a margin for error of 8.67. Approximately, you can add 2 to that and get a sigma. So this is a method with a sigma of over 10. If I change accuracy, so you could come into the simulator and you can change the mean from 104 to 115. Now you can see that it still passes here. However, the risk level is higher. Now you're reporting 13 patients in a month, 13 medically unreliable results in a month, and now your margin for error is much smaller. So you can glance at this report and see what's going on, and with the simulator, you can model a change in precision, a change in accuracy, you can change the allowable error limit, you can say, what if I use biological variation, and you can change the acceptable risk level. Once you have your margin for error, then look beyond the stats. Come over here and select the number, type, frequency of testing and criteria for acceptable results of the quality control. So based on the margin for error, you would choose a QC process. In this case, the margin for error is above 3.5. I'm going to use a 1-3S rule. If my margin for error is only 3.3, I'm going to come here, I'm going to use, okay, I changed this myself to a 2.5. It would recommend a 1-3S, but if I want to, I can use a 2.5, and I would, yeah, okay, we're gonna just stop that one right there. You can use whatever you want for your QC rule. You get to select them. So as the margin for error changes, the QC strategy changes. If you have a margin for error of 1.33, you're going to use a 1-2S as a reject, you're going to increase the QC frequency, you're going to increase the chart review, you're going to increase the supervisor review, and you're going to do something to make it better. This, by the way, folks, a margin for error of 1.33 is a sigma of 3.3. You match the QCP to the margin for error. As the margin for error goes down, the power of the QC rule, the QC frequency, the chart review, and the action go up. And if risk is unacceptable, stop. That's something that's missing in a lot of QC processes. There is a time that you absolutely must stop. So now we've selected the QC rule. And in this case, I'm using a 1-2S rule, although it looks like I don't need to. So I could have improved my examples, pardon me. But it shows here the QC rule that I've selected will mathematically optimize QC, detect acceptable risk in the first run. Yes, it will. This is a simulator. This is a thing you can play with. It's a very simple tool. You come in here and you say, how many flags did I see? I saw 20. It's going to detect risk in one run. In this case, it's also going to detect risk in one run with the existing QC process. So here's what is recommended. The more QC chart is the recommended QC process, and it compares it to the assigned mean, the assigned SD, and the intended QC reject rule that you're using. Let me slow this down a little. On this page, you're going to fill in these numbers. You're going to put in the assigned mean, you're going to put in the assigned SD, and you're going to put in your intended QC rule. So the assigned mean is 104. My assigned SD on the chart is 3, so my 2SD comes in at 110. But if you look over here on the more chart, the SD is assigned at the real value of 1.5. Why am I doing that, becomes the question. Well, there's a very good reason. We default in the simulator. You can change it to what your actual mean in SD is assigned on the chart. The problem is that very, 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 very few labs, as a matter of fact, I don't think I've seen one, I've heard of one, where they actually put the measured mean in SD on the QC chart. So these are 33 study labs that we studied recently, 16 from the year 2000, 17 from 2012 to 2014, 545 QC samples, 12 analytes, and most people are assigning their standard deviations at double the actual. And it hasn't changed in 15 years. This is a study I did back in the year 2000. The problem is, and the problem that's not being addressed, is how people are actually doing QC. It's QC in practice, not QC in theory. If you choose the QC rule, so as the analytical process becomes better, as the analytical quality process becomes better, as the current risk becomes lower, then the average number of runs to reject to the first QC flag after we simulated that clinical failure, there is a very clear relationship. As margin for error becomes lower, as the risk becomes lower, the number of runs to reject becomes lower if you choose the right QC. But this is what people are doing now. This is that same study that we presented at the AACC poster. Most labs, a lot of this, a huge proportion of the data I look at will never flag a clinically significant failure, and there is absolutely no relationship in the QC practice between the analytical process quality and the QC process effectiveness. 605 QC samples, that same group we looked at earlier, from the year 2000 and 2014, and we also had a control group from the year 2000. So we've got two comparisons here. There's a mix of old and new lab methods. In this set, this is the lab QC practice. 33% of the results would detect a clinically significant error in one run, 30% took 2 to 10, and the runs to reject was, they just simply never, it was more than 10, there was never a QC reject in over a third. Over a third. That means for this 605 QC samples, you could just as well have poured them down the sink as doing the QC test on them, because the QC was set up in such a way that they would never detect a clinically significant failure. If you go through this mathematical optimization, you eliminate all of that, but the more interesting thing is that you cannot eliminate these. You cannot eliminate these tests that take 2 to 10 runs to detect an error. And that's the scary part, and those are the ones that you really need to identify, and you will identify. So you come down to your final assessment and plans. You've looked at, so you've gone through 4 steps. You've entered the data for the current risk. You've selected the QC process. Now, and then you've compared the existing QC process and you've judged the runs to reject for both processes. Now you come into a final assessment and plans. You do a risk analysis, so you look at the estimated risk. Now in this case, it was going to take you 20 runs to detect change. You would never detect it. If that method failed this month, you would report 12,000 patients who were exposed to unacceptable risk. They don't all get medically unreliable results, but they would all be exposed to an unacceptable risk level, because if this method rose above the acceptable risk level, you would never detect it. So 40% of the patients tested after this failure to unacceptable risk would be exposed to unacceptable risk. And then you evaluate that risk and say, is that okay? You compare it to if you used the mathematically optimized process. Now, in this instance, you actually need to increase your QC frequency, because this is one of those analytes where it's going to take 3 runs to detect the error, because the method is challenged to meet the medical goals. You get into something like sodium and you will see this often. But you can manage the optimum QC frequency to say no more than the acceptable risk. The acceptable risk level specified by the lab director will ever be exposed to unacceptable risk. So what we're calling this is mathematically optimized risk evaluation. It compares the current measured risk and the potential risk, if the method fails, to acceptable risk levels defined by the lab director. When you have those numbers, it's a simple mathematical calculation. So the reports show you, is the current risk acceptable? Is the potential risk okay with your existing QC and with the mathematically optimized process? You can model QC frequency. So you can say, what happens if I run my QC 60 times a month? Now, this isn't an instance, this is a great test. You're going to detect the error in the first run. I'll only expose 1.7%. But if I drop that down to 30 tests a month, I'm going to expose 1,000 patients to potential risk before I test the next QC. That means 3.3% of my patients might receive a bad result. People are talking about decreasing the amount of QC, but until you check the QC, how many patients have been exposed to risk? So I saw something the other day that talked about looking at statistical QC once a month. How many patients are you going to report in between? And you remember that thing we said about, you have to check the results that, you should be checking up on all the results since the error occurred. So you can bring this all into a risk assessor's report. It shows you, is risk acceptable to the risk manager? What action is planned? If you're the medical director, the clinical chemist, you come through and you stack these up and you go through and you sort them out just by what the risk manager has done before it comes to you. Does this QC sample meet the medical goal and acceptable risk level? How many medically unreliable results are currently reported each month? That's a typo there. That should say medical, by the way, where it says laboratory goal. Is the existing QC process effective to alert staff to unacceptable patient risk? Can you reduce risk by optimizing the QC process? How many patients may receive medically unreliable results at what clinical cost if the method fails? And what are the net potential healthcare savings? The QC data you have sitting around in your lab can tell you all of this. And on a single page report, you can visualize the acceptability of current risk, the ability of your existing and QC processes on one page. So you start, is risk acceptable to the risk manager? Who's the risk manager? They're the person that oversees the entry of, and that should again say the medical goal, the acceptable risk level, the measured values for each QC patient, for each QC sample, and then they follow the algorithms in the simulator. They select the QC process, they assess the pass-fail evaluations, they examine the risk and cost, Here, they are determining the risk-based quality grade. This is done automatically in our Quality Optimizer software, and they select appropriate action to reduce risk or costs. What are they going to do? They can choose from a checklist. You can change the checklist, but all of these may be appropriate actions. Finally, you have a process in the process of quality control. You can look at one little part of this report and just see current risk is acceptable, potential risk is not acceptable. And you can see the numbers behind that. This is the premise that the QC sample was tested to represent patient samples with a true value of 100 units. Our medical staff and scientific recommendations concur that results between 80 and 120 are relevant, accurate, and reliable for patient care. Current risk is acceptable, potential risk is not. What are the financial implications? The estimated current cost is $0, but if 5% of results after this failure fail, you don't know how many are going to fail after a hazardous event occurs or after a failure occurs. But if it was 5%, then 415 fewer patients would receive medically unreliable results, saving $20,793 in clinical or legal costs from incorrect or delayed treatment. Where did that come from? It came from your estimate of the average cost of a medically unreliable result. And that is a difficult number to set. We've sort of set it normally at about $50, but the cost of a glucose that fails the 10% limit is very different than an HIV that is reported as a false negative. There's much to be done yet with this process. But you can calculate, based on the numbers you put in, what are the clinical implications, what are the financial implications. So you start, is risk acceptable to the risk manager? And you can see here, no, it's not. They've graded this as a risk-based grade C. Does it meet the goals? It passes. Current risk is acceptable. You're costing nothing in lab errors right now. Your potential risk fails with the existing QCP, can pass if you mathematically optimize it. It is not acceptable, and if you mathematically optimize QC, if the method fails, you would save $1,300. And you can see what it looks like, and you can see that the existing QC process is going to take 2 runs to detect the error, where the mathematically optimized will only take 1. So where do you go to from here? You poor folks, people are telling you go here, go there. You have a lot of decisions to make. But effective, efficient QC is clear, simple, and easy. It really is. You can do this if you just polish here, put in some education and some software. Let the software do what the software absolutely must do. This process is too complicated to teach people. It is certainly too complicated to teach your frontline techs. However, those reports will tell you improve precision, improve accuracy. Here's exactly the action you need to take. So the bench tech can come and get those reports where the risk manager has said, here's what you need to do. And from our automated software, it's going to tell you improve accuracy, improve precision, change your QC process. Where can you learn more? If you go to AwesomeU at awesomenumbers.org, you can check here, make sense of risk management, and you'll find lots of videos and references there. You can actually purchase this IQCP ToolKit. After years and years and years of preparation, we are ready to release it today. And if you purchase by midnight to receive it tomorrow, you can purchase it for $99 as opposed to the $150. This is a reasonably priced solution. This can let everybody verify the effectiveness of your quality control. At the least, the effectiveness of QC to detect medically allowable error, should be evaluated. And this will let you do that. Wow, that was a record. Do we have questions?
Hi, Zoe. Yes, we do. We have a few questions.
Excellent.
Our first question is, does risk management need to be performed for calculated measurements, i.e. MCH or MCHC?
That is an excellent question. And I would say that if the processes that are used to calculate MCH and MCHC are working, there's no way that they can be wrong. However, it would be a very interesting study to throw them through here, because if they're both acceptable but both off a little bit, the processes that are creating those calculations, might the combined effect be unacceptable? So I think not, but I would like to study it first. And one of the things I'd like to see happen at Awesome Numbers is people get together to answer these things yourselves, you know, to work on it. You've got the tools now, but throw some of these things through, get together, collaborate. I think if you're waiting for somebody else to give you a solution to risk management, they're not going to do it. But I'd love to set something up to study that.
Okay, our second question. If I have an extended period of time that requires amended result notification, but unable to retest because of instability, how should I handle it in a risk management perspective?
Oh, I like that question. Let me see if I've got my favorite answer here. Okay. Most QC processes expose one patient run to risk because we report the results before we check the QC. If you want to have zero risk, all you have to do is check the QC before you report the results if you're sure that the QC you're using will detect that error. So suppose you've gone through this process. If you want to avoid that, if you've already sent them out and they're unstable, then you're in trouble. So that might be an instance where you want to check the QC before we send out the patients. If we go through, like I report run 1, I report run 2, now this is bracketed, but when I report run 3, we get a QC flag. What if this system took 3 days to detect the error? If you've verified your QC process, you know that this system will take 3 days to detect, or 3 runs to detect error. You've tripled your QC, and you've checked the QC before the method has left, before the results have left the lab. You can manage risk at any level you want. You can manage risk at 0%, but you need a QC process that is proven to detect risk, and you need to check the QC before you report the patients.
Okay, our final question is, how is analytical QC quality applied or interpreted in methodologies such as ELISA testing to detect a clinically significant failure?
Yes, we're actually working on that, or some of us are. Your problem when you get into the ELISAs and the infectious diseases and so on is things are not quite as simple and not quite as linear. And again, it comes back to study it. I would take this simulator and throw the numbers through it and see what they do. What I'd like to see happen is for people to get together and form some discussion groups here so that we can work on these things. And, you know, I don't have time to do everything, but you folks, I can give you tools and I can give you a place to connect so that we can have projects that people can come together to do and put together teams. Because everybody's asking the same questions, why not get together and help each other find the answers? I think this will work there. I think the premise is that if you can get these 5 numbers, so what it comes down to is, can you set this medical goal an acceptable risk level? That's the question. Do they work with the same, and medical goals have always been assumed to be a plus minus where really they're often, you can go maybe 10 units low and 3 units high. This is, I hope, the start of an evolution of better quality control. When you start looking at it from this perspective and you start automating it, then you can answer a whole new raft of questions. So next step is to use this and gather some data together. If we have no more questions, I would just leave you with this. Oh, is there another question?
No. If you you can also submit any other questions you have, obviously, to our awesomenumbers.org website, and we would be happy to answer them as well.
Yes.
And just a few final comments. Once again, the IQCP ToolKit is available for purchase today for $99. The simulator will be available tomorrow. We'll be finishing it tonight, so that'll be available tomorrow. So it's $99 today for pre-purchase, and tomorrow it will be available for $150. And that's about it. And do you have any other comments, Zoe?
No, I think that's it. I thank people so much for being here. I would love to hear your comments. This is, we're taking a new step. I think this opens up new capabilities. I think the one question that we will send out in the follow-up tomorrow is, or two questions. If you could do this, would you do it? And what stands in the way of you making this happen? If we have the technology to put in these 5 numbers and a few other facts and automate risk management, what stands between us and doing this? I guess is my big question that I'd like to pose to you as a challenge. And maybe we'll start a blog. Ray, what do we do? We have a blog or something we can talk about that?
Sure, we can definitely have a blog. Absolutely, we can do that. We have one. We'll have one at awesomenumbers.com anyways, but we can also set up one at our AwesomeU site.
All right, we'll send you news about that with tomorrow's email too. But again, I think that's it for me. I thank you very, very much, and we hope to hear your experiences as you use this simulator. Have a great day.
And yes, can I just make one final comment as well? If you have any difficulties with purchasing from the store, if you want to purchase our product, and you have any difficulties, please send me an email and I can get back to you right away. Okay, thank you very much. And thank you, Zoe, for the presentation, and we'll sign off. Thank you so much. And thank you for everyone for listening.
Bye, all.